Hi, in today's video you're going to get an introduction to LENR technology. I'm going to tell you what it is and you're also going to see an experiment. I'll tell you about the equipment I'm using and what I'm trying to achieve. So first of all, LENR stands for Low Energy Nuclear Reactions and it's a new field within material engineering and nanotechnology that potentially could allow us to produce better and smarter materials, but also produce energy that is cheap and clean, energy that doesn't produce any carbon dioxide or deadly nuclear radiation. LENR builds upon cold fusion, something that gained recognition back in the 80s after Martin Fleischmann and Stanley Pons announced that they had been running electrolytic experiments containing heavy water and electrodes of palladium, and sometimes after running these experiments for a few weeks they saw that their systems started to produce excess amount of energy. In fact, they produced so much excess energy that they could not explain this by a chemical reaction, so people thought it had to be a fusion reaction taking place, fusion on a tabletop. Today, this field of studies is known as LENR, and it's kind of an indication that we're not really sure what's going on, and it could be fusion, but it could be other nuclear reactions that hasn't been known earlier. Alright, so let's start the actual experiment. What you're seeing here on the picture on the tabletop, on the left side you have the electrical equipment and the electrical safety shield, and in the middle you have the reactor housing, the white reactor housing with the two ports where the actual experimentation and measurements takes place. This is a kit that we provide on our webpage for only $250 for those who wants to perform these experiments at home, in their garage, or we also sold some to reputable companies and governmental scientists. The first thing I'm going to do is connect the mains cable to power up the systems. I'm also going to set the temperature of the PID to the operational temperature, which is I'm going to set the value of 700 degrees. Because I did some calibrations before running this experiment, I know that a PID temperature of 700 degrees is equivalent to 900 degrees Celsius operation temperature within the pods. Now all I need to do is switch the pulse width modulation to full and the system starts heating up. The PID is efficiently the brain of the system, and it works very much like the thermostat in your home. You set a specific temperature, it'll take the temperature of the system up to that value and it'll keep the temperature there. Because of that, this system actually has some automated functionality built into it that very easily allows you to determine if you're producing excess heat or not. The PID is connected to a thermocouple. That's like a thermometer that's baked into the rear of the reactor housing, located close to port 1. Port 1 is where you're putting your control sample or maybe an empty quartz tube. So you use that as a control to see what temperature you're actually working on, but both ports, they are connected in serial to each other. They receive the equal amount of input energy, and you would expect the temperature to stay the same between the ports, unless port 2, where you're actually putting your active fuel sample that you have prepared, unless that produces some excess heat anomaly, you'll see the temperature go up in that specific port. While I was running the calibration, I noticed that this particular system had a high electrical resistance. It wasn't heating up very fast, and also it didn't want to go to higher temperatures. Normally there's a very easy fix for this. You just shorten the length of the super Kentel heater wires located in port 1 and port 2. But you know what, I'm a lazy guy, so what I did instead was to take some ceramic wadding, putting it putting it inside the quartz tube of port 1 and port 2 to isolate the system, prohibiting heat to leave it. And yeah, that pretty much solved my problem. So that was a easy fix for me. You can now see how the display of the PID is showing a temperature of around 90 degrees centigrade, meaning that there should be a temperature within port 1 and port 2 of about 250 to 300 degrees centigrade. So there's a big offset. We just started the reactor up and the heat haven't permeated the reactor housing to reach the thermocouple, which is connected to the PID. Also, the higher you go in temperature, the more accurate your reading is going to be, the offset is going to be smaller. And you also want to run this temperature for quite some time to level out the temperature wherever you're going for. When you do so, you'll see the readings tend to be very, very accurate. One of the most common questions we get about this system is how much heat can they resist? The reactor housing should be good, working in temperatures up towards 1500 degrees centigrades, while the quartz glass tubes within the pores and the reactor cores, they should withstand at least 1600 degrees centigrades. The Parkmol cement works well at 1200 degrees centigrade. We don't know how much heat it can take. Basically, we haven't maxed out the system, but we haven't had any problem. The limitations are probably the superheater cantle wires because they start softening around 1400 degrees, and also the K-type thermocouples that we're providing with the systems. They're only intended to measure temperatures up to 1350 degrees. When you order the basic LENR test kit from our webpage, it comes pretty much complete with everything that you need to hit the ground running. The kit includes the reactor housing and its support stand, the quartz glass reactor tubes, prefabricated heater cores, and a few empty reactor cores. We also provide the electrical equipment such as the PID, a 36 volt AC to DC power supply, a pulse width modulator that we're using as a dimmer, and the solid state relay that acts as a switch, allowing a current to either run or not run through the system. To make the kit affordable, we do not include the high temperature data logger that I'm using in this video. Instead, we provide a basic digital thermometer display that allows you to measure ambient room temperature or the temperature of the thermocouples mounted inside the reactor housing. You can also connect one of the 3 K-type thermocouples that comes with the kit and use the display to measure the temperature within one of the ports of the reactor. Remember though, the display doesn't record any temperature, so as soon as you're getting addicted to the system, you're gonna want to get the high temperature data logger kit as well. All cables are included except for the mains cable. This is because the standards of the plugs varies from country to country. These cables can be bought for just $1 or $2 in your local hardware store, or even better, just cut the cable from one of your household appliances that you're not using any longer. When you order the kit, make sure that you have access to refractory cement for sealing the reactor cores, as well as the chemicals you're intending to test. If you want to test your own chemicals, that's fine, but we also provide a wide selection on our webpage. Some of the chemicals often used in LENR experiments can be expensive and difficult to obtain unless you're registered as a company, and sometimes even then. So be aware there are merchants out there on the internet that will sell you chemicals of inferior quality. Sometimes you're not going to get whatever it is you're ordering, or anything at all. To look for radiation in my laboratory, I'm using the GC10, a very popular Arduino-based Geiger counter. The GC10 can detect gammas, X radiation, as well high energy betas. Obviously, this is not just for protection. We're using the GC10 to determine if an anomaly might be taking place in our experiments. The GC10 does not record data on its own that you can transfer to a computer and plot out in charts. If you need that functionality or any other functionality, we can build custom-made data logger kits based on your specific needs. If we take a look at the display of the PID right now, It shows a value around 300 degrees centigrade, which should amount for a temperature in the ports between maybe 550 and 600. The temperature is increasing more rapidly on the PID, and this is because the temperature are now catching up, reaching to the thermocouple baked into the back of the reactor housing. So from now on, moving forward, for every minute, the offset will be less between the poles of the reactor and the PID. One of the obvious advantages of this system is the swappable cores. Whenever the system has reached its operating temperature and you have performed one measurement or one experiment, you can just remove one of the reactor cores and insert a new one. Within 5 to 10 minutes you can start a new experiment. When you put in a new reactor core, the temperature of that port will fall by around 100 degrees centigrade, and the system will need maybe 5 to 10 minutes to catch up and even out in temperature. So this is kind of a pim-pam system which you just can keep going. You can do 10 or 20, 30 experiments in one day if you have your reactor cores prepared. Of course, this depends on how long time you want to run one experiment, how long you want to collect data. But really, with this system, amateurs can perform as many ECAT type of experiments in one day as some professional teams does in months, even years, and that is to a fraction of the price. Other setups that are built to make the same test as the LENR test kit tends to use more expensive materials. They're also often all included as well, meaning that if one of the components breaks down, the whole systems become worthless. Let's say you make an experiment and you want to remove the powder and send it for analysis. The last thing you want to do is to destroy a reactor that might have taken you days or even weeks to build. Another problem with all-included reactor designs can be preparing and pre-baking the nanopowders used as fuel. Because we rely on swappable cores, we can bake and prepare many of them in a furnace at the time, rather than pre-baking one fuel sample at a time inside of a reactor. Seriously, there are thousands of unknown combinations of tests that need to be explored. So, unless it can be avoided, and unless you're sure you have a recipe that will give you the result you're looking for, you really don't want a setup that'll take hours to start every time. The initial inspiration for this system, although the design has been revised many times, is the experiments performed by Russian scientist Alexander Parkhomov back in 2014. He built all-included reactors using heat-resistant refractory cement. When testing his reactors, he submerged them in water and calculated their efficiency based on how much water they evaporated. What impressed us the most was the cost of his reactors. While other teams would spend sometimes more than $1,000 per unit, he'd build a reactor for less than $25. Of course, compared to the LENR test kit, I'd never bother with a Parkhomov. They must have been very time consuming to build, and you'd had to build a lot of them probably to get one that would reach the operational temperature without leaking or breaking down. So even compared to old school Parkhomov, this is a much more cost efficient system. If we take a look at our experiment heating up again, we can see how the pores of the reactor is now glowing due to the immense heat. The display of the PID is showing a value of close to 440, while the high temperature data logger is showing a value close to 415. So that makes a offset of 25 between the thermocouples baked into the back of the reactor housing located close to port 1 and port 2. I believe that as we continue increasing the temperature, this offset of 2025 will continue. However, percentually, the offset is going down over time. If we take a look at the Geiger counter, there's nothing really interesting going on. We have a background radiation that's, around the 20 counts per minute. In my workspace, it goes as low as 15, but I've seen it go up hitting 41, 42. Because we are the new guys, most people hasn't yet understood really what it is that we're setting out to achieve. Instead, we're being compared with the more established MFMP, the Martin Fleischmann Memorial Project. They are just as us an open science initiative, with the difference that they perform experiments streamed live over the internet, which we do not. What we are trying to achieve is to broaden the field. LookingForHeat.com is not just sharing information, but we're also sharing our innovation. So instead of having 2 or 3 people performing a live experiment stream over the internet with 1,000 people following and commenting, we are making the materials, the equipment, and the chemicals readily available so that more experiments can take place at any given time. This is, we think, a good alternative and a way forward. If you're not familiar with the work of the MFMP, I would really recommend you to check out their webpage, www.quantumheat.org. By selling, we also try to provide a channel for funding for independent researchers who needs a source of income. If you buy, for example, the LENR test kit, a certain proportion of those resources goes back into the community, helping whoever helped us to develop the kit in the first place. Some people have a theoretical mindset and some people have a practical. Don't get me wrong about this. We do need people's advice and expertise on whatever it is we should be doing, so please keep posting all them comments. However, if you're a practical guy, we're the ones to help you get started. Not one person alone can bring LENR to the market, if possible doing so. We believe it has to be a team effort. If you think you can make your own experiments, please consider to order a system for us. We take your money and we give you something for something. However, if you want to support our work without making experiments, please consider to make a donation on our webpage. Let's talk a little bit about the fuel powder composition we're using in this test. The palladium deuterium researchers have worked very hard for years to narrow down some of the mysterious conditions that they think are necessary for LENR to take place in the first place. For example, they have told us that to achieve LENR in a palladium environment, one of the conditions is to load, which is to say infuse or pack hydrogen into the palladium. Both palladium and nickel is similar in that sense, capable of soaking up huge amount of hydrogen. In palladium research, you'll have no chance to see excess heat unless you reach a loading of at least 85%. They've also determined that the low energy nuclear reaction seems to take place mainly close to the surface of these materials. A simplification of the overall idea is, I think, to pack hydrogen atoms very closely together within the metal lattices to achieve a very rare environment. You then stimulate that hydrogen metal lattice and hopefully a reaction will take place. When someone tells me that LENR is not possible and should not even be tested in the first place, I often use the symbolism of flying cows. While it's commonly believed that cows don't fly, actually under the right extreme conditions, cows are known to have lifted from the ground. One such condition is when a tornado takes place. In LENR, we're using nanomaterials and material engineering to create very extreme environments on the atomic scale. To justify why I even bother in the first place, I refer to reputable companies and institutions such as Toyota, Mitsubishi, ENEA, and NASA. Instead of using nickel ingot, in this experiment I'm using high purity nano-nickel powder. There's some logic to this. The fine nickel particles in my reactor have a surface area larger than a field of football if you stretch it out. This should increase the probability of LENR reaction taking place, but also it will help with the loading of hydrogen into the materials. Remember, because this is a nuclear technology and because there are billions of particles in my small fuel sample, I only need a few reactions to occasionally take place in order to produce substantial amounts of energy. A nuclear reaction is 1 million times stronger than that of a chemical. The nickel has as well gone through a separate pre-treatment process known as hydrogenation. 70% of my fuel sample is nickel particles. The rest is comprised of 20% lithium aluminium hydride as well 10% lithium metal nanopowder. One of the key processes in our pre-baking was to first heat up the empty reactor cores to a temperature of 800 degrees to reduce oxides that might exist within the materials. Therefore, to be diminishing or drowning the reaction by bonding with hydrogen rather than letting hydrogen load into the nickel. Normally, we'll do this in bulk using our high temperature furnace, but as I want to show there's an alternative this time, I use the pores of the reactor as a furnace, just to show it can be done. The next step is adding the fuel composition into the reactor cores. Preferably, you should be working in a glove box when doing this. You don't want to breathe in these chemicals. I've seen in videos where people are smelling the chemicals. Please do not do that. As you can see in this clip, I didn't have a glow box when filling up the cores. However, I was very careful and I only worked with small volumes. Now on to the sealing. We have a foolproof guide on our webpage for how to apply and mix the cement to seal the reactor cores. It's really easy. It's time to pre-bake the reactor cores and curing the cement. We're not going to high temperatures, so if you lack access to a furnace, you can use an old oven. I bake these cores 1 hour at 150 degrees centigrade. This is to have the lithium aluminium hydride give off some of its hydrogen that hopefully should have been soaked up by the nickel. After that, I increase the temperature to 200 degrees for an additional 30 minutes to further cure the cement and continue the loading. While baking the powders, there are various chemical reactions that can take place. This is especially true with my fuel powder, which has notable exothermic chemical reactions taking place at temperatures of 150, 200 and 400 centigrades. This is to say that at these temperatures, energy is released, just as it is, for example, when you strike a match. Because I'm looking for nuclear heat, I'm happy to shed that chemical produced heat energy from my reactor cores before starting an experiment or collecting any data. Most LENR experiments right now uses nickel, hydrogen and lithium. If this all seems easy to you, it's not. You have people who have studied this material for 20 or 30 years and yet they continue to learn new things about them all the time. Honestly, most of the time it's more advanced than I'm showing here. Remember, this is LENR for Dummies, it's just an introduction. It could turn out that if you have a good trigger, the recipes and the processes can be simplified. Although not necessarily easy, is having two slightly out of phase lasers massage the materials. We have a few lasers. I hope we find time to get around and use them someday. With the basic LENR test kit, you can't really measure the drop of pressure when loading hydrogen into nickel. You would have to upgrade your reactor with, for example, a dog bone tube. This is just a base you can add to. For example, if you add a so-called H-bridge to the system, you are able to create various funky waveforms which will allow you to affect how the metal lattice oscillates. Looking at the screen of the data logger, we can see that one of the sensors is producing an error value. This is because I've only connected one high temperature thermocouple to the data logger. There is no problem with the equipment. The data logger stores data on a CSV file that opens up in Excel. If one of the thousands of data points that we have recorded today should show an error value, we're not going to be able to draw up a chart or plot. Instead, Excel will ignore any column that has the value error in it. Now and then the data logger can miss one data point. This happens, for example, when the data logger is powered by batteries running low Or if we move the data logger and the two high temperature thermocouple wires accidentally come in contact with each other. I'm sure there is an easy fix for this, but I'm using Plotly online for free anyways. Unlike Excel, Plotly will still produce the chart, it's just going to ignore every error data point. The process of migrating your data from your data logger is very easy. As soon as the data logger is powered up, it will start record data until you shut it off. Every time the data logger is turned on, it will create a new CSV file and automatically record your data. To plot, all you need to do is remove the SD card and then access the CSV file on your computer. This is how the raw data look. Hover your mouse pointer over column A and click once to select the whole column. In the upper menu of Excel, choose the Data tab. Now click on the button saying Text to Columns. A new window will open up. First click Next. We now have some options for how to separate the data. Make sure the Comma tab is chosen. Click Next again, and then Finish. Bada boom, bada bing. Our text is going to be easy to work with or transfer to any other software. Except for the two high temperature thermocouples. This data logger records ambient temperature, date, and time. You can also connect it to the electrical circuit of your LENR test kit to have it record voltage and current as well. Alright, reaching a value of 695 on the PID. As we're getting closer to 700, you'll see the red little LED light on the PID display blink. This is because the system will intermittently tell the power supply to shut off in order to regulate the temperature and keep it at 700. It's normal for the system to overshoot 5 or 10 degrees before it stabilizes at the value that you have chosen. But because the system is intelligent, over time it's going to learn to better stabilize on the value that you've set for it. Background radiation is normal, so I'll give this system a few minutes to stabilize in temperature. And unless I see a temperature continue to climb within port 2 of the reactor, I'm going to just leave it for 1 hour. When I come back, I'll see if there is a divergence in temperature. Should there be a divergence, we see heat is forming in port 2 of the reactor, I'll continue the experiment. If not, I'm just going to shift the reactor core in port 2. I hope that you enjoyed watching the video and that you now have a better basic understanding of LENR and also the Model T test kit.
Looking for Heat Internet Store. We sell cold fusion components and complete kits to scientists and engineers. But we sell t-shirts and books to the general public. We like to share the knowledge. The store is Looking for Heat, a place where down-earth people can meet and watch videos, you can't beat it. Engineering, we will share your secrets. The store is Looking for Heat, a place where down-earth people can meet and watch videos, you can't beat it. Engineering, we will share your secrets. We are selling advanced materials, chemicals, measurements, equipment, and lab equipment. Also power supplies and many other things for engineers and scientists around the world. Come to Looking for Heat.